Thank you for the kind introduction. Well, first, I would like to thank the organizers for the kind invitation to talk here today. My name is Tom Depover. I'm an assistant professor at Ghent University in the research group of Sustainable Material Science. And today I will talk about hydrogen trapping and embrittlement evaluated in martensitic iron, aluminium, carbon steels. I would like to thank my co-authors of this work, Professor Verbeke, who is heading our research group at Ghent University, also Professor Springer from the Max Planck Institute in Düsseldorf, and WTH Aachen for the very nice collaboration. And then especially our PhD student, Marco Pinsen, who was in charge of all the experimental work in this study. So today I will start with introduction, and then I will focus first on the iron carbon steels without the addition of aluminium. I will both talk about hydrogen trapping and hydrogen embrittlement. And then I will continue with the addition of aluminium. I will first focus on what is the effect of adding aluminium to the microstructure. And then I will also discuss on the impact of aluminium on the mechanism of hydrogen embrittlement. So let's start with an introduction. Well, high strength steels and high strength levels are required to increase durability and performance of steel components. We want to go as a challenge to lighter, better performing and more sustainable materials. And therefore, the group of Hauke Springer has developed a novel alloy type where aluminium is added to go for a lightweight design due to the lower density of aluminium compared to iron, of course. This was proven to be very cost effective, and the resulting microstructure was a martensitic matrix with including copper carbides. What was also tested was the corrosion resistance of these materials. Well, they resemble quite a bearing application, so therefore it was compared with the conventional bearing steel as shown here, and it was clearly observed that the iron, aluminium, carbon steel showed a better resistance against corrosion compared to the bearing steel. The composition of the aluminium grade was 1.1 carbon and 8% of aluminium. Well, as you might know, in bearings, a lot of lubricants are used, and these are all oil-based, and these can decompose due to heat generation. Well, because of that, hydrogen can again be taken by the microstructure. And then the question was, of course, that the interaction between these martensitic iron, aluminium, carbon alloys with hydrogen is unknown. And that's where we come into the picture with the SMS research group to investigate this specific topic. As a second part in the introduction, I want to focus on the microstructure, because here we deal indeed with the martensitic microstructure. And as we know, these martensitic steel grades, they come with high strengths, but they're also quite prone to hydrogen embrittlement. Why? Well, because it's a quite complicated microstructure containing both high angle and low angle grain boundaries. As high angle grain boundaries, we have the prior austenitic grain boundaries, but also packet and block boundaries are present in the microstructure as shown in the figure. We also have low angle grain boundaries like the lead boundaries that resemble more like dislocations. Next to the quite complex microstructure, we also have additional influencing factors. For instance, the chemical composition, possible inclusions like alumina or MNS, and the grain size, the prior austenitic grain size. Well, this hinders the complete understanding of the underlying mechanisms. Therefore, we focused on a quite fundamental approach to systematically target these materials and evaluate their trapping and embrittlement behavior. Few challenges were faced. Well, the proposed alloy contained quite a large carbon content and aluminium content, as already explained. Now the question is, how does each element influence the interaction with hydrogen? Well, then our approach was to do this in a systematic way and to work with simplified iron carbon alloys. So this was our solution, and we did not only target one material, we did a bunch of alloys, and we evaluated both the influence of carbon and the influence of addition of aluminium. So as you can see in the first row, the effect of the carbon content on the hydrogen embrittlement mechanism will be evaluated. This will be the first part of today. So there we'll focus only on iron carbon steels. And in the second part of today, I will also discuss on what is the role of the addition of aluminium. So this is this point, the effect of aluminium content on the mechanism of hydrogen embrittlement. The other alloys are currently ongoing in the PhD of Marco Pinson to validate the proposed mechanisms and to optimize our reasoning and understanding. A second challenge was that these high carbon martensitic steels are quite brittle. Normally we use in situ tensile testing to evaluate the sensitivity towards hydrogen embrittlement. As you could see here, this was in a previous publication from 2016. Here we compared different generic materials containing perlite, ferrite, but also bainite, and we compared two different carbon contents. So B2 stands for 0.2% of carbon, B4 is 0.4% of carbon. This was possible, but when we then go from bainite, so the B, if we go to M, to martensite, it was possible to do in situ tensile testing when the content of carbon was 0.2. So for M2, we can see embrittlement when you compare the air tests with the charge tests. But as you can see, there is no graph of M4. M4, containing 0.4% of carbon, was also tested, but this was impossible as the samples already broke upon clamping or very fast during the tensile test. So there is no way to evaluate embrittlement for very, very brittle materials, which are martensitic. So that's why we developed an in situ bending setup with electrochemical charging. Again, in situ, because we don't want to lose hydrogen in between charging and testing. So this is the introduction. Let's now focus on the interaction with these iron carbon steels and the hydrogen interaction with them. So without the addition of aluminium. What do we have? Well, we have 0.2, 0.4 and 1.1% of carbon. These materials were produced by vacuum induction melting under an argon atmosphere and then cast and hot rolled until 1.1 millimeter. After that, we austenitized the materials around 100 degrees C above their AC3 temperature for 20 minutes, and then following by a brine quench to obtain a martensitic microstructure. For the 0.2 and 0.4 carbon material, this was completely possible, but since carbon increases the critical cooling rate, we had to increase the austenitization temperature for the 1.1 material. There we went a bit higher, we went to 1000 degrees as austenitization temperature for the 1.1 because we wanted to avoid the formation of second phases like troostite. So that's why the temperature of austenitization was a bit higher. And this also explains the prior austenitic grain size that was obtained. So it was quite similar for the 0.2 and 0.4 carbon steel. Around 30 microns was the prior austenitic grain size. But for the 1.1, this was about 70. And this is linked to the increased temperature during austenitization because this was needed to avoid second phases. As you can also see in the 1.1 carbon steel, we have quench cracks. Quench cracks appear due to thermal stresses in the steel when the carbon content is larger than 0.7 weight percent. Since, of course, the appearance of plate martensite is required there. Next to that, also when the carbon content exceeds the iotic composition, you can have cementite along the austenitic grain boundaries upon hot rolling already, and this facilitates also cracking, as you can observe in the 1.1 microstructure. So there we have quench cracks. The hardness values are nicely in line, so we're increasing with carbon content. And what we also observe is that we have 13% of retained austenite present because of the stabilizing effect of the carbon addition. So there we have retained austenite. It's quite important. I will not focus too much on the 1.1. There is a dedicated study published in Material Science and Engineering A if you want to know more about the role of quench cracking and retained austenite in hard carbon steels. Let's now move to the interaction with hydrogen. So there we tackled this with PBS measurements. PBS was done on the three materials, and here you can see the results. So what do? We charge a sample with hydrogen, we bring it to a furnace, we apply a specific heating rate, in this case 1200 degrees C per hour, and we record the hydrogen evolution. You can see for the 1.1 carbon steel in blue that we have a quite high temperature peak. This is linked to the presence of retained austenite, as you remember from the previous slide. This retained austenite contained hydrogen and released its hydrogen upon heating. This is not detrapping from austenite. This is actually the phase that was decomposed because of the temperature that was applied. This was proven by XRD measurements before and after the TVS, but also by BSC measurements, where phase transformation that take place can be recorded, and that can result in a peak, which is related to the energy that is required for the dissolution or formation of a specific phase. So this is then a proven result that retained austenite was responsible for the high temperature peak for the blue material. Not from deep trapping, but because retained austenite decomposed during during the temperature ramp. Now, for today's talk, we will focus on the low temperature peaks because they are important to explain the embrittlement behavior. And as you can see, the content of hydrogen is increasing with carbon content. And let's now move a bit forward, because here we are dealing with materials which show quite high diffusivity. And this comes with a certain challenge, let's say. As you can see in the experimental data, we have quite a large jump in the beginning. This is because we keep the time in between charging and testing as short as possible, because we don't want to lose hydrogen. If you wait longer times, you don't have this quick jump, but then you also lose important information. So we keep the time in between charging and testing to 1 minute. 1 minute to clean and dry our sample, and then we can implement it into the furnace. But because of the very high diffusion, you can see a very quick jump at 20 degrees C. And this is then followed by a slow decrease. As you can imagine, deconvoluting such a spectrum which shows this high jump is quite challenging and quite complex. So this is why we extrapolate the peak. So we know that we have 1 minute in between charging and testing. So we know how much hydrogen is lost during the 60 seconds in between charging and testing. And then the experimental data is then further treated by an exponential extrapolation towards lower temperatures, as can be seen in this graph. This is done by taking indeed into account the content of hydrogen that was lost in between charging and testing. And this resembles very weakly trapped hydrogen linked to interstitial hydrogen. So then we have treated our data and we can do deconvolution. So here you can see the deconvolutions of the TVS data for the 0.2, 0.4 and 1.1 carbon steel. And we can make this deconvolution. And then you can see that we have several peaks available, one from dislocations and the high angle grain boundaries, and also for the 1.1 carbon steel, we have a peak linked to second. This is not that straightforward. A lot of tests are done, a lot of repetitions are produced, and of course, different heating rates are needed to calculate the activation energy of the trapping site. What is also needed to take into account is that the amount of hydrogen, so the area under the peak, should be the same independent of the applied heating rate. So these are restrictions and things you have to take into account when you do such deconvolution. If you do this with a lot of care and by coupling it with the microstructure, you can be sure about the trapping site. It's not because you obtain an activation energy of 30 kilojoules per mole that you can say this is dislocations because literature tells me so. You need to know your materials, you need to change the microstructure, and then only you're sure about what you see and how you can deconvolute such a spectrum. Dislocations come with an activation energy of 27 kilojoules per mole and the high angle grain boundaries with 37 kilojoules per mole. What did we do to verify this? If you take a look to the right bottom, you can see indeed that the content of hydrogen was determined under the peak by taking the integral. And you can see that indeed the content of hydrogen trapped at these locations is increasing with carbon content, with increasing indeed the carbon content in the alloys. When the prior austenitic grain size was the same, about these 30 microns for the 0.2 and 0.4 carbon steel, the content of hydrogen was similar, but when the high angle grain boundaries were lowered, because indeed the prior austenitic grain size increased to 70 micrometers, this also comes then with a lower hydrogen content. So this is a proof indeed that the concentration of hydrogen is then reduced because of the larger grain size. Next to that, we did also embrittlements. So here you can see the bending test that was developed, in situ bending, where we apply a force and then evaluate the embrittlement. I will speed up a bit, so I'll continue to the results. So here you can see the results for the air test and the hydrogen test of the 0.4 and 0.2 carbon steel. So this was done until 40 millimeters of extension, because from that point onwards, the support points change. And this was done on saturated samples at 1 millimeter per minute. So here we can clearly see and evaluate embrittlement. So the 0.4 carbon samples was not able to evaluate by in situ tensile testing, but with in situ bending, we can really tackle and evaluate embrittlement of these materials. And if we then inspect the fracture surface, we can clearly see in the air tests that we move from microvolt coalescence in the 0.2 to an intergranular type of fracture for the 1.1. But when we charge with hydrogen, we have the additional presence of cleavage indicated by the green arrows. So in the 0.2, we can see this cleavage facets, but also in the 1.1, we have a change from intergranular to cleavage when hydrogen is present, which is quite contradictory to what was stated before. So this is quite interesting to discuss. So what do we see here? Indeed, that we have a transition to a cleavage type of fracture when hydrogen is added. Next to that, we also have additional hydrogen-induced cracks, as shown by the red arrows. What is the reason for this? Well, the martensitic blocks and packets, they are embrittled by hydrogen. This is the reason why we observe fracture as cleavage and not as intergranular trapping, intergranular failure because of trapping at the high angle grain boundaries indeed. If we go back to our system, you can see here the representation of the martensitic matrix consisting of prior austenitic grains. If we now focus and we take a look to the block boundaries, what is really happening is a decohesion. So here you can see indeed that hydrogen can weaken the block boundaries and can lead to quasi-cleavage fracture. This is a result in the case when we have some plasticity, in the case of 0.2. This is a result of both localized plasticity and also concentration of hydrogen at packet or block boundaries, which are high angle grain boundaries, but also indeed because of the high angle grain boundaries that hinder dislocation movement. So this is then the mechanism responsible for failure because of indeed TDS indicated that hydrogen was trapped at dislocations and high angle grain boundaries, and then the packet and block boundaries were the weakest link. I will move now to the aluminium addition. So in this case, we add aluminium to it. So for the 0.4 carbon steel, we have the same microstructure, but in the case of aluminium, we see a change at the interface between the different grains. We see like some opening, some delamination. We didn't know it was present there. When taking a closer look, and I have to thank here the people from the Max Planck Institute in Düsseldorf, Michael Herbig and Saurabh Mohan for these measurements, we could see that in figure A, we see needle-shaped dark regions at the prior austenitic grain boundary. And the darkness indicates that the regions contains a lower dislocation density compared to the martensitic matrix. In B, we can see the dislocation structure based on ECI data. With the EBSD, you can clearly see that no gamma was present. So this is not austenitic, this is purely a ferritic film that was formed. So it's not delamination, it's not open space, it's a phase that is present at the grain boundaries at the prior austenitic grain boundaries. So aluminium additions as a ferrite stabilizer causes the formation of a second phase on the grain boundaries. And the second phase has large dislocation density, its BCC structure, and is softer than surrounding martensitic matrix. How did we tackle that? By performing nanoindentation. So as can be seen in picture E, you can see 100 indents. If you take a clear look, you can see a lot of indents, which are separated 10 microns from each other. And this comes down with a certain hardness value. Hardness value indicated by the color map, going from 3 to 8 gigapascal. If we then plot the prior austenitic grain boundaries in black, we can clearly see that there are green regions, and these green regions, they come with a softer phase, and they are indeed the locations where we observed in the previous slide these open spaces. So these open spaces in between the grains, in between the prior austenitic grains, they are a ferritic film, and they make it softer. And the reason for this can be found in the continuous cooling diagrams based on models of Kirkaldy and Badisha, showing that indeed at a quite fast quenching, 220 degrees per second, we crossed the ferritic nose in the case when aluminium was added. So Aluminium as a strong ferrite stabilizing element upon quenching will nucleate at the grain boundaries. And this, of course, has an effect on the failure and also on the ductility and strength of the materials. These CCT diagrams took into account the chemical composition, the austenitization temperature, and the prior austenitic grain size. What we can see then is indeed that the ferritic microfilm, because we have this ferritic microfilm when we add aluminium, shown in the blue curves, leads to an increase of ductility. So the presence of the ferritic microfilm increases the ductility. And when we use the same heat treatment for the 0.4 carbon, we also had a benitic microfilm, and this worsened the behavior then. So this clearly shows that the ferritic microfilm shows a beneficial effect, and this yields, of course, opportunities to increase the ductility of very hard and brittle materials by inventive grain boundary engineering. If we now take a very close look to the fractal surface, we can see here, we can see these microvoids. You can see this presence of very small microvoids which are dispersed over the underlying martensitic microstructure. So you can see underneath the microvoids, you can see the martensitic microstructure, and on top of them, you have like a very fine film of ferrite that transforms in a ductile way, and that acts as a glue in between the martensitic grains. For ductile materials, the presence of such a ferritic microfilm is quite harmful since it lowers its strength as well. But for brittle materials, the gain in ductility is then paired with also the possibility to reach a higher fracture strength. So it's positive. And also in terms of hydrogen, if we now take a look through hydrogen, we can see that for the iron 0.4 carbon material, we obtained cleavage fracture when hydrogen was present. This was because the packet and block boundaries were the weakest link, leading then to failure, as proven by the TDS. In the case when we add aluminium, you can see that we have an intergranular type of fracture, which is a bit better and coming with a larger extension. So the presence of the microfilm redirects the fracture propagation along the microfilm. So now in this case, it's not the packet and block boundaries that are the weakest link, but it's the interface between ferrite and the martensitic matrix, which is now the weakest link when aluminium is added. And this delays sample fracture, as can be seen from the curve coming from about 2 millimeter extension without aluminium to 3 millimeter extension when aluminium is added. Quite a lot of information, so I'm looking forward to the interaction afterwards and to have a nice discussion. I will conclude the presentation now. So we have developed a new in situ bending methodology that allows us to investigate the mechanisms of hydrogen embrittlement, also in high strength, low ductility, martensitic materials. For instance, the iron aluminium carbon steels. In the case of the martensitic iron carbon steels, so without the addition of aluminium, we know that hydrogen is trapped at the high angle grain boundaries and at these locations. Hydrogen causes there a transition to a cleavage type of fracture, so coming from a microvoid coalescence and intergranular fracture type and a mixed type for the 0.4, we go to cleavage type. Why? Because the weakest link is the martensitic packet and block boundaries that were able to trap a lot of hydrogen, as proven by the TDS. When we then add aluminium, well, this aluminium addition causes the formation of a ferritic microfilm along the prior austenitic grain boundaries. So we have this very fine microfilm of ferrite that can act as a glue. And this ferritic microfilm increases the ductility of the brittle martensitic steels. This was then proven by the ECHI, EBSD, and nanoindentation tests. And next to that, also the microfilm causes a delay of the hydrogen-induced fracture since it redirects the crack propagation along the ferrite-martensite interface. These results presented today were based on the following publications. So 2 of them are published and 2 of them are under revision and will have to be submitted based on the work of our PhD student, Marco Pince. I'm looking forward to your questions. If we still have time or during the break, I would thank you for your attention. Thanks a lot.